computer. Yep. And we shall begin. So recording's turned on. Next thing I remember to do is share my screen. So we should have my screen shared there. And let's see if Blackboard is up and running. I'm doing this mostly to check that I have all the links put together. That's our warning. If you go to Blackboard, it says on January, we're going to try to fix something. Basically, Blackboard is going to break on Friday. They've scheduled 2 hours of maintenance Friday morning. It'll be unlikely for them to complete it in 2 hours. So if you have anything that's due in your other classes on Friday, you might want to get it uploaded Thursday night before they break everything. Oh, Guy, look at this is what puts food in your bowl and litter in your litter box. There you go. All right, I believe I've just connected to the wrong class. So let's try that all over again. This is that class. And I do not have lesson 4 connected. So let's go ahead and do that. Apologize for doing this on your time. So lesson 4, and the topic of lesson 4 is St. Venant equations, in particular momentum. And I hope we'll do a little bit of a workshop today. Oh, looks like I thought they were breaking Blackboard a little extra early. And then in here, we go into the directory, and I'll go ahead and put up the web link. And let me get to the correct web link. So today should be this guy. Yeah, that looks correct. Really need to get these index pages built better. All right, one last action. So if you hear your other professors complaining about Blackboard, or if you happen to be using it yourself as a assistant, you'll know why everyone that uses it complains about it. Because you notice I'm having to do stuff one file at a time. That's because it was made by professionals. Okay. I want to put this into the other one. Huh. So it is currently broken. Copy the directory. Want to copy to the other class. It literally is refusing input. Looks like the Friday's breakage is occurring a little bit early. That is seriously bizarre. I'll have to do that in the other section. Because of reasons I don't understand, they have this course broken into 2 sections and they were incapable of linking them. So there I am complaining some more. You can hear a lot of that. And it refused the space. And a balance in a workshop. Web link. For the life of me, don't know why the copy didn't work. Okay, so it now should be the same on your Blackboard account, regardless of whether you're in DO1 or section 10. So from the home page, you go to lessons, go to lesson 4, click on the content server link, and it should take you here. And what we're going to start with is the presentation. And this directory's got a whole bunch of stuff in it. I'll show you what we're going to use in a second. We're actually going to look at this particular file, lesson 4, development HTML. And a few other ones are now extraneous and I haven't tidied it up yet, but let's go on that one. And so this one is our hydraulics review. We're continuing and we're going to look at momentum conservation today. And then the workshop, we're going to make our initial forays into trying to use JupyterLab to do some relatively simplistic calculations to help reinforce the ideas that we are articulating here. Recall from our last meeting, we went through a definition of breaking up a river or stream into a collection of interconnected computational cells, and then we analyzed one of those cells arbitrarily and ultimately arrived at a conservation of mass equation or continuity, depending on what you want to call it, same idea. And it ultimately resulted to dz dt, which is the change in the water surface elevation with respect to time, is equal to times the top width as a function of depth. And in this case, z is measured from the bottom of the computational cell. Oh, come on, dude. Seriously. Plus dq dx, which was the change in discharge as we move upstream or downstream, is equal to whatever lateral inflow, which was given the value lowercase q. So this is one of the 2 equations of the St. Vernon equations. The other one comes from the conservation of linear momentum, and that's what we're going to start to examine now. So the conservation of momentum is the statement that the change in momentum in a reach, in this case a computational cell, is equal to the net momentum entering the cell plus the sum of the forces on the water in the cell. As in the mass balance, we'll look at each component separately for clarity and then assemble them at the end. So the figure here is the figure that we're going to use for coming up with the equation of motion, or the momentum equation. And in the figure, the upstream face of the cell is here, where the cursor is moving up and down. The downstream face is here, and this is somewhat more conceptualized than the cell last time. The channel slope is represented by this x-axis, and the slope relative to the horizontal is indicated here by the angle alpha. The distance between the upstream and downstream face is this value delta x. Think of it as it's delta x. And the momentum entering on the upstream face is rho, the specific weight of the liquid, multiplied by the velocity, multiplied by the discharge. And if you recall from your fluid mechanics class, that actually is a momentum term. And the momentum leaving is equal to the momentum entering plus the change with respect to x. So whatever the change in momentum moving from the upstream to the downstream face is, so that's the d by dx of rho v q. Within the computational cell, we're keeping track of the weight of the water, indicated here with the W, and whatever the frictional shear is. So my cat is being attention grabbing right now. The frictional shear force is indicated by this arrow with the symbol tau next to it. The other forces that are not depicted in the sketch that are going to play a role are the upstream pressure force and the downstream pressure force. We've actually got the gravitational component embedded here in the weight. The significance of this angle alpha in this triangle that's drawn here on the picture is simply that a component of the weight is pulling the water downslope towards positive x in this drawing. And so this angle alpha here that's labeled is the same as the angle alpha here, formed with a vertical segment and a segment that is perpendicular to the bottom of the channel, which forms this triangle right here. So with that in mind, and unable to keep it on the same screen, let's look at the momentum entering the left side of the sketch. So it's written there as rho q v, but we can also write that as rho, the density of the liquid, multiplied by the velocity squared times the area. And that's the structure of momentum we're usually familiar with from our engineering mechanics classes, and that's the structure of momentum that we get in a fluid mechanics class, but they're the same thing. The momentum leaving on the right side of the sketch is rho qv, the same as the momentum entering, plus whatever change in momentum there is moving across the cell. So partial with respect to x of rho qv multiplied by that distance delta x, which can be rewritten substituting the variables as rho v squared area plus partial with respect to x of rho v squared area multiplied by the distance delta x. The momentum accumulating within the cell is also known as the rate of change of linear momentum, and we depict that as follows. dl dt, where capital L here is the linear momentum, is the same as the derivative with respect to time of mass times velocity, that's within the cell, which is equal to the partial with respect to time of rho, area times velocity, times delta x, and taking the portions of the term that are not going to change temporally out, we'll assume the density is constant with respect to time. The size of the cell doesn't change with respect to time, so we have rho delta x times partial with respect to time of area times velocity. So we now have three parts of our equation. We have the rate of change of momentum in the cell, the momentum entering the cell, and the momentum leaving the cell. And we're treating momentum as if it's just some quantity, just like we did mass last time. It could be a dissolved chemical. The underlying balance equation is the same once we substitute the appropriate variable descriptions. And now we're going to examine the various forces on the element. The first obvious one is gravity. And the gravitational force on the element is the product of the mass in the element and the downslope component of gravitational acceleration. The mass in the element is rho times the cross-sectional area times delta x. So the cross-sectional area, if we move that a distance of delta x, that produces a volume. And then if we multiply that volume by the density, rho, that produces a mass. So dimensionally, mass per length cubed, a length squared term, and a length. So what we have left is mass. The x component of gravitational acceleration in our drawing would be g times the sine of alpha, which for small values of alpha is essentially equal to the slope s sub 0. So the sine of alpha will be replaced with a bottom slope for relatively small slopes. The resulting force of gravity then is the product of these two values. So the force of gravity on the liquid in the computational cell is rho, the specific weight of the liquid, times g, the gravitational constant, times the cross-sectional area, as yet unspecified, multiplied by the bottom slope, which is playing the role of sine of alpha, multiplied by delta x, which gives us the correct volume for calculating a mass. So force of gravity is literally mass times acceleration of gravity there, replaced with half the letters of the alphabet. Why don't you go be Schrodinger's cat and half here and half somewhere else? You're not going to. Okay, well, at least get out of the way. Oh, they're seeing the screen, so you're just up here in the upper right-hand corner. Enough out of my way so I can read. The frictional force is the product of the shear stress in the contact area. And in the computational cell, or the reach here, the contact area is going to be the product of the reach length and the average wetted perimeter for the reach. And so we can write that as the frictional force is equal to tau, which is the shear stress, multiplied by wetted perimeter, P sub w, multiplied by delta x, which is the length of the reach. And in this case, where P sub w is the area over the hydraulic radius, and a good approximation for shear stress in unsteady flow is the shear stress is rho times the acceleration of gravity times the hydraulic radius multiplied by the friction slope. So essentially we're saying shear stress is some kind of Manning's type equation, or you can think of it as a quadratic friction model. The value S sub f is the slope of the energy grade line at some instant, and conventionally is called the friction slope. It's empirically determined by a variety of models. Typically, Chezy's or Manning's equation is used. In either of the two models, we're ultimately going to be using a steady flow equation of motion to mimic unsteady behavior. There's nothing wrong with that. It's common practice. But that decision does, in some sense, limit the frequency response of a model, which imposes further limitations in the case where we want to examine how things behave when change is rapid. The resulting friction model, after all that, is the force of friction is equal to rho times g times the cross-sectional area times friction slope times delta x. And this is all still for just one computational reach. The pressure force is the next one, and we'll get to it immediately. But it's actually fairly elaborate, and it's elaborate in the sense that it uses a lot of letters of the alphabet, and then in the end, most of them cancel each other out. But for the sake of trying to be faithful to the original derivations, we'll keep track of all the things as we go and then cancel them out at the end. So the figure here is a arbitrary cross section, and we're measuring from the bottom to the water surface. And so if I had the ability to color this in, that would give us our cross-sectional area. And if we measured from the bottom up some distance h, not necessarily all the way to the top, but to some depth within that water column, and then define a very small rectangular panel of height dh, the top width function would give us how wide this thing is. And the product of how wide that is times this dh gives us a differential area, dA. The distance from the free surface down to the bottom or the centroid of this panel is z minus h, where in this description, z represents the distance from the bottom of the channel all the way to the free surface. And the reason this drawing exists is you can imagine that we can start with a panel here at the bottom, compute its dA, and then add that to the panel just above it, just above that, and integrate from bottom to the free surface to recover the total area and correspondingly the pressure force. So the pressure force on that object right there is the integral of the area of dF, whatever the differential force is. So imagine we have this panel here and we know how deep it is. If we know how deep it is, we know what the pressure is, because pressure is rho g times the depth into the liquid. If we know the area, that pressure times that area produces a force. And then we move the panel and do it again and again and again until we've done all the panels from the bottom to the top. When we're done, we have the total pressure force on that cross-sectional area. So in the terms of this drawing, the differential pressure force dF is z minus h. So that's giving us the depth downward into the liquid, times rho g, which is the specific weight of the liquid, multiplied by squiggle of h, and I'll explain what squiggle is in a second, although it's actually probably got a real Greek letter name, but I don't know what it is off the top of my head. Times dh. Dude, you can't keep doing that. Excuse me for a second. Out. Yep, I'm here. Okay. That should be better. And you just witnessed a rarity, a cat actually following instructions. So get back located. There we go. So I think I was on a squiggle of h. So squiggle of h is the term I'm using for the width in this cross section as a function of depth. So squiggle right here at the bottom has a value of 0. Squiggle up here at the top has a value of whatever the top width is. And as you move up and down in the geometric section, the numerical value of squiggle will change. And so squiggle of h times dh gives us this dA function. Z minus h times gamma is what gives us the point pressure. And so the product of the point pressure and the differential area is the differential force. And then we integrate overall values of area, we recover the total force. It's like I said, it's elaborate. It's an awful lot of letters of the alphabet to get to when we get to the end, what it's going to look like. So the net force is the difference between the upstream and the downstream forces. So the force of pressure net on the water in the computational cell is the pressure force on the upstream minus the pressure force on the downstream, or F sub P minus F sub P times the partial with respect to x of the pressure force multiplied by dx, the length of the computational cell. And when we cancel out the terms that negate themselves, as positive F sub P and this negative F sub P, we have the net pressure force is the change with respect to x of the pressure force in the cell multiplied by how long the cell is, dx. So when we express that using the integral, we have minus partial with respect to x of F sub P dx is equal to minus partial with respect to x of the integral from 0 to z. So we're integrating from the bottom to the free surface of the specific weight of the liquid, rho g, z minus h, how deep we are in the liquid, squiggle of h, how wide the panel is, dh, how tall the panel is, and we're doing that over, over the length of the cell. And we can evaluate that doing integration by parts. So the net force is minus rho g, partial depth with respect to x of the integral from 0 to z of squiggle of h dh plus the integral from 0 to z of z minus h squiggle h partial with respect to space of squiggle dh dx. Okay, so now we're really getting into the letters of the alphabet. The point is that term right there integrates to the cross-sectional area. This point right here is the variation in pressure with position along the channel. And that takes care of 2 of the 3 forces of interest. The third force is the pressure force induced by the banks. And I'm going to switch video for a second to make a quick sketch of what's meant by that. And then we will return to this picture. So I go to stop sharing. I switch my camera. So if we're looking in plan view, and I'm intentionally drawing the channel that way, and we have our upstream and downstream section. So here's our flow. We essentially have this portion of the channel walls are exerting a pressure force as well as the change in geometry from the upstream to the downstream face. So that last integral is expressing the pressure that's exerted by the channel wall that's not necessarily perpendicular to the flow field. Okay, so that's just being complete. It's not one of those things that we necessarily can easily evaluate. So the expression I just attempted to draw is taken care of by this term. And so let me stipulate that we have the way to represent a bank force, and we have the way to represent the net change in pressure between the upstream and the downstream face. So now we want to put everything together into a conventional momentum balance. We basically have listed out the forces and we've listed out how we're going to represent momentum. So again, recall from your engineering mechanics class that one way of representing momentum change is momentum in minus momentum out plus the sum of the forces on the object is equal to the change change in momentum with respect to time. If we substitute the parts that we have just put together, momentum in minus momentum out equals the net pressure force plus the bank force plus the gravity force minus friction. That's going to equal the change in linear momentum with respect to time. And now we'll make the substitutions for each piece. Momentum in, momentum out, net pressure force between the upstream and downstream face, bank force, gravity, friction. Seriously, how come it doesn't want to obey? There we go. Friction equals the net change in momentum in the computational cell. So if we want to reiterate that, the rows in that expression in order, they represent, the first row represents the net momentum entering the reach. So it's momentum in minus momentum out. The second row represents the pressure force differential at the end section. So it's the change in pressure by virtue of each end of the computational cell having a slightly different geometry. The third term represents the pressure forces exerted by the channel sides onto the liquid. The fourth term is the gravitational force. The fifth is frictional force opposing flow, hence the minus sign as written. And the sixth term is the total acceleration in the reach expressed as a change in linear momentum. So now let's simplify that so it's humanly useful and doesn't just make mathematicians get all giddy. So first we will cancel terms that can be canceled and divide by rho delta x. The division set is us stipulating that it's isothermal and we can treat it as incompressible flow and the reach has finite length. So with that in mind, the momentum equation can be simplified to minus partial with respect to x of v squared times a. So that's really a spatial change in momentum. That's like a convective acceleration term right there. Minus g partial z partial x integral from 0 to z squiggle of h dh plus g a s0 minus g r s sub f, making the substitutions for those terms, equals d by dt of a v. You'll notice that parts of the bank pressure force term and parts of the end section pressure force differential vanished. It's because that term and that term are the same, even though the order of the integrand appears changed. Because dx is finite, those can be interchanged, and so those two terms have canceled. So what's left on pressure is simply the area integral. We will make that substitution, noting that this integral is simply the cross-sectional flow area. And so now our equation simplifies into minus partial with respect to x of v squared a minus g dz dx times a. So dz dx is the slope of the water surface in the element, GAS0, gravitational acceleration, GAS sub F, frictional resistance to flow, finally the local acceleration. The term with the mean section velocity squared, so this term right here, we'll expand it using the chain rule of calculus. And I have a YouTube link if you don't know what the chain rule of calculus is, but I'm pretty sure you do. But I recommend you look at the YouTube link, not necessarily because of chain rule of calculus. It's done by a let's say performer, a content creator named Nancy Pai, who was an MIT math graduate, and she started this channel 8 or 10 years ago to just teach interesting stuff on calculus, and it's actually it's pretty cool. She's soothing if you're having trouble sleeping. I'm out like a light in about 2-3 minutes tops, unless the math actually gets interesting. But I don't know about you. For me, math is a tool. It's not that interesting. So I find it's a fun thing to watch. And if you have younger siblings in your family that are struggling with math, you can legitimately turn them on to that. And it's a real YouTube channel. It's done a little bit better than Khan Academy, but she had 15 years of technology in her favor. So expand using the chain rule, and then we're going to use continuity to replace a few terms. So we have our continuity equation back here. We can remember Q is V times A. So we'll keep that in mind. We'll use that to replace some elements in the momentum equation. So doing so, the expression becomes the following: minus partial with respect to t of AV. That is a acceleration term. So we have the change of velocity with respect to time, classic acceleration. We have a term A dv dt plus v dA dt. So that is the chain rule that's replacing that term, is equal to A dv dt minus VA dv dx minus v squared dA dx. And so now we have an expression right there that can be used to substitute in this term. If we expand and then insert, we can construct minus v squared dA dx minus 2 VA dv dx minus GA dz dx plus GA S0 minus S sub F. So that's our gravity friction term. And what we've done is we've expanded a lot of the other forces. And this is literally just calculus here, is equal to A dv dt minus VA dv dx minus v squared dA dx. And if we examine that, we'll see that there's a minus v squared dA dx over here and a minus v squared dA dx over here. We can make them go bye-bye. Ta-ta, so long. And there is a minus 2 VA dv dx here and a minus 1 VA dv dx here. So one of those VA dv dx's on the right side removes the existence of one of those VA dv dx's on the left side. So what remains is minus velocity times area times the change in velocity with respect to change in space minus gravitational constant of acceleration times area times the slope of the water surface, dz dx, plus g times the area times the difference in the bottom slope and the friction slope is equal to the acceleration of the liquid inside the computational cell. So that equation that we have highlighted in parts, I'll highlight the whole thing. is the form of the momentum equation that has practical use. And we'll rearrange it in the remainder of the presentation to fit a few other purposes. But that is the expression of momentum in our computational cell in the channel reach. So that equation combined with the continuity equation from last time provides the necessary tools to be able to predict the depth of water in a channel over time based on the boundary conditions of whatever the end depths are and whatever the lateral inflow is. So if we make a little bit more manipulation, we can get it into a form that looks like the following. Minus velocity divided by gravity times the change of velocity with respect to space minus the change in depth with respect to space. Think of that as the slope of the water surface, plus the slope of the bottom minus the friction slope is equal to 1 over g times acceleration. And if we rearrange that to put the two slopes on the left-hand side and the remaining part of momentum to the right-hand side, the result is the following. S0 minus S sub f equals 1 over g dv dt plus dz dx plus v over g dv dx. And now comes the cool part. I think it's cool. I didn't do this myself. This is copied almost verbatim out of Stern, possibly with changes of the letter of the alphabet to make it my own. If the local acceleration, the first term on the right, so if this term is 0 and the depth taper is 0 and the convective acceleration term is 0, then the expression degenerates into the algebraic equation that we call normal flow. Bottom slope equals friction slope. And you would have had that in various versions in your hydrology classes. Certainly in my hydrology classes and water systems classes, we use that tool a lot. So when you learn Manning's equation, that's literally what it's representing. It's the case where convective acceleration, depth taper, and local acceleration have all vanished. And it's called normal flow. And essentially it says the friction slope is the same as the bottom slope. That's a handy bit of information in a flow regime, because if that's true, computing discharge based on flow depth and known geometry is pretty straightforward. It's called the slope area method. You've done it probably dozens of times, maybe even hundreds of times. That is a good starting point. If, on the other hand, the depth taper is no longer 0 and the convective acceleration term is no longer 0, but we still have the property that the local acceleration term is 0, so the dv dt term is gone, we basically have a situation called gradually varied flow, which you've also had in both those classes that I just mentioned. That happens to be an ordinary differential equation, and it normally looks like friction slope is equal to bottom slope minus depth taper minus convective acceleration. The last part is if those things are not 0. If all the terms are retained, we have the equation that says friction slope is equal to bottom slope minus acceleration minus depth taper minus convective acceleration. So number 3 is retains most of the letters of the alphabet. You can take it on faith that of the 3, it's the most difficult if we have to do the computations ourselves by hand. So if we couple the two equations, so if continuity and momentum are coupled, that coupled set of partial differential equations are called the St. Venant equations, after some dude named St. Venant, I imagine. I'm going to go look that up on the internet because I actually have no idea where the name comes from. And I know it's burning in your mind too, so we'll go ahead and look it up. St. Bet you he's going to be a Benedictine monk that's more noted for his ability to make a tasty after dinner beverage. Published in French by Saint Venant. So Saint Venant was indeed a person named after Jean-Claude Barré de Saint Venant. Let's go look up what there is to find out about Jean. So he's an old dude. He's from the 1880s. Stress analysis. He was a mathematician. Saint Venant was just his family name. That's kind of cool. I thought he was a real saint. It's good to know that the Vatican wasn't wasting their sainthood on people that could do Navier-Stokes equations. So he was a contemporary of Navier and Stokes, and looks like he was also a contemporary of Boussinesq, another name you may have heard of. And he taught mathematics at École des Ponts Paris Tech. So where he succeeded, so he came after some dude named Coriolis. So okay, he's a pretty important dude in this kind of stuff. Let's get back to the. Oh, I really shouldn't have done that. I can't even find. I guess that's it. There we go. So looking at these two equations, if we find solutions, which would be functions in the z time plane and in the velocity time plane, and those functions may not be anything that we can analytically imagine, but if we have a collection of z and t and v and t that are correlated, those are called solutions to the two equations, and those are what we're seeking, because those will give us the ability to predict the velocity as time and the water depth as a function of time. That has obvious engineering utility. We find those functions through a variety of methods. I've listed just a few here. Finite difference, finite element, finite volume, method of characteristics. I think there's a few more. There's Markdown Cell. They're all computational. And the reason they're computational is, whether you can tell it or not by looking at it, those are hyperbolic partial differential equations. So they have a lovely property that under certain conditions their solutions don't exist, and there certainly are no analytical solutions for them. What we're going to proceed with in this next couple of class meetings is we're going to go ahead and we're going to use finite difference, because it's probably the simplest to explain, and if you've never done it, it's certainly the simplest to learn. And you'll have to take it on faith that the other three are quite similar. And if you can understand one, you can surely teach yourself any of the other two. The method of characteristics as a domain solver is not used much anymore. But in the 1970s, when I went to college, God, that's kind of a scary thought. That was a big deal, because it was the only tool we had that was effective. Characteristics are still used to deal with boundary conditions, but in the central part of the solution domain, we don't bother with characteristics. And the reason they're not used anymore, the downside of the method of characteristics is your computational grid is changing shape every step of the computation. And so it had a bad habit of, as your computation proceeded, your process was moving out of the domain of interest. It predates the electronic computers that I'm using right now and you all have access to. So at this point, you've now seen sort of a pseudo derivation of the Saint Venant equations. The key caveats is that this is for one-dimensional only. If we went to higher spatial dimensions, we would have to deal with how momentum moves in both spatial dimensions and how momentum is transferred from one direction to another, because it is. Continuity is trivial going to higher dimensions. It's just a few more letters of the alphabet. Continuity is not a problem. But the momentum term, when we go to 2 or more dimensions, gets quite a bit more complex. Also, when we go to 2 dimensions or higher, we are now introducing not just linear momentum, we have to keep track of angular momentum, and stuff starts to spin. So generally in the higher dimensions, the preferable way is to solve everything with as a scalar called curl, and then recover from the curl, which you had in fluid mechanics, the actual x and y components. When we have to do that, we use other people's software. It's that stuff, you have to trust me, is difficult to program. So obviously I can't do it, so I'm not even going to even attempt to show you. So that's the main issue, is the one-dimensional thing. The other big issue is that we can try to fake it, but this is not very good at capturing shock waves moving through the system. And that is because of the way we represent our friction term. Because that friction term is actually a steady flow friction term, shock waves are not properly modeled using that. That's change we could make if we had a need to, but again, that's very special case, and you at this point would have probably no trouble teaching yourself how to do it. Might take a week or two, but you could figure out how to alter that. Okay, so I want to take, good on time, I want to take a few minutes to kind of foreshadow where we're headed and get a little bit started on our workshop. So I have here in the scripts in lecture, there we go. So it doesn't look like much. So what we're going to do is, over the next couple meetings, is we're going to go through these. We're going to build some water surface profiles to convince ourselves we know how to operate these various algorithms and ultimately produce backwater curves. Rather than just show that, I want to actually go to the trouble to build it. So what we're first starting with is steady uniform flow. Now, if we look at that, I actually can read this right now because I know how to read. Is uniform flow is defined as a situation where the friction slope and channel slope are the same. In this kind of flow, the profile grade line and the hydraulic grade line and the energy grade line are all parallel. So that says the friction slope is equal to the change in head with respect to x, which is equal to the bottom slope. So all that's really pretty straightforward. We could apply a Darcy-Weisbach model to adapt it for non-circular conduits, and then we can get correlations of the friction factor or the more common Chezy loss model. And so that's all fairly straightforward. Where steady uniform flow actually gets amazingly tricky is if you're going to try to concoct a simple example. Because even though that looks simple, if our goal is to determine water depth for a given discharge or given discharge for water depth, it turned out that wasn't as easy as I thought. It's not that hard. So let me turn off that, and I'm going to show a definition sketch. Now my cat wants back in the house. So let's see if I can change my view. Well, as much as I like to see other people, I wanted to. Can you all see my screen? See, I'm not sharing my video screen. Where my hand's moving, there's a drawing there?
Yeah, we can see the drawing.
Yes.
Okay, cool. Let me see if I can get it a little bit clearer. That's the best I'm going to get. Okay. So let me point out to it before I draw on it and destroy my beautiful artwork. So let's discuss that first flow regime, uniform flow. So here's our channel bottom. It's brown. And it has a bottom slope S sub 0. And we're looking at 2 points on it, position x1 and x2. The height from the bottom, from the datum to the bottom of the channel, I've written here is z1. I may regret that variable choice, but we will proceed anyway. The height here is z2. The flow depth, so the distance from the channel bottom to the water surface, is y2 in this point, y1 up here. And then here is a blue line that's supposed to represent our water surface. And this is uniform flow. So the slope of the water surface, the slope of the channel bottom, and the friction slope in red are all the same. And then the remaining distance is the velocity head at each end, v1 squared over 2g, v2 squared over 2g. And in steady flow, v1 and v2 for prismatic geometry should be the same. So as a way to get ourselves started in trying to get a handle on the hydraulics of computational hydraulics, is want to go through developing a tool that will, in some essence, make those calculations easy for me. So this is one of those cases where it's really easy to do by hand and incredibly hard to figure out how to do in a computer in a simple way. But that's a good place to start because we'll use parts of these for the other two parts of the class. So let me return to screen sharing. If I remember how to do that, it's down here at the bottom. I got this ginormous screen and I still can't find anything on it. It was a lot easier on a little teeny screen because nothing could hide from you. Couldn't see anything, but it couldn't hide from me. Okay, so I should be sharing my screen again. And so what I wanted to do is go to something called Workshop. All I have in Workshop is, this is as far as I got this this evening before the started class. And I'm trying to create a uniform flow example. And then we'll go ahead and do the example in swim will be almost trivial. So I want to build these functions, and let me get to, dang it. Thought I had it already loaded. So I'm now going to go to my programming environment, which is the JupyterLab on another computer. So you should see my Windows-like looking screen, and I'm going to ask you to be patient with me because Windows is my fourth operating system that I've used today, and it's not my primary one, so I get a little confused with it. Yes, cats, I know that you're starving, but you just have to wait a little bit longer. They're pretending that they're starving. Because if you have pets, you know exactly what I mean. You can feed them plenty and they're still always hungry. There we go. Actually, this is a really good environment. Because it's so slow, it keeps me from going too fast. Maybe not so much for you guys, because you're not freshmen just out of high school coming to college for the first time, but definitely in my freshman class, I go too fast. The following errors occurred. That's not good. Well, this might be a really quick workshop. If I can't get the software running on my machine, there'll be no point. That's promising. That's what I wanted. And possibly in my lifetime, it'll do it. Okay, we don't want to do that because then that'll bring us up a window management thing and it'll request a credit card. Okay, that is an undergraduate class. Let me delete it. So I'm going to create a new directory for this class. I'm going to call it ce5362. Okay, so that's computer stuff. You don't really need me to show you that. I want to create a notebook, and what should we name this notebook today? So that was a real question. Somebody come up with a name.
Workshop 1.
Workshop 1, okay. Thank you for playing along. Workshop 1 it will be. Every now and then you get a group of people, someone will give a smart aleck name like Fred or Judy. I actually like that when they do that because that is the proper level of cynicism for doing engineering workshops. So let's, part of this workshop today is I have no idea if you've ever used JupyterLab or not. So we're going to do just some simple stuff and ultimately build it into a nice little computational package. Then we'll compare it to Swim, and then we'll never use the workshop again, the JupyterLab again. So so the key things of this particular interface, there's a file system browser over here on the left, and you can move up and down the file system by clicking on these little doodles up here. There is a notebook entry area, and it uses the concept of cells. So I'm pressing the plus button, I'm adding cells to my notebook. Similar to an Excel spreadsheet, it evaluates the cells from top to bottom, but only when you tell it to, unlike a spreadsheet, which is always evaluating in an attempt to go ahead and hit the spinning beach ball and lock up your system. The cells come in different types. There's a code cell, a markdown cell, and a raw cell. Code cell is expecting some type of code. So when you run that cell, you have to have syntactically correct, in this case, Python code. Otherwise, it will generate an exception and issue you an error message. Doesn't break anything. It just turns pink and it's very scary. Another type of cell is called a markdown cell. That's basically a text cell. So the last three presentations, actually all the presentations for this course so far were created in a Jupyter notebook using markdown cells. So I'm using that as a word processor. It's not the best word processor, but it does pretty good stuff, and it has a reasonably effective ability to do mathematical typesetting, which makes it attractive. And then raw cell, it just stores the text. It doesn't do anything with a raw cell. So a raw cell is a convenient way to put stuff in that you're not sure is going to work right or not, and you don't want to break things. You just use it kind of as a placeholder. So this first cell is a code cell, and I'm going to create a function. Let's just do a depth area function for rectangular channel. I'm going to see if cut and paste is going to work. Let's give it a try, copy. So I'm moving off. So this is a server coming to my home machine, going back to a server. So I don't know if cut and paste is going to work, but let's see. Paste cells is not what I want to do. Oh, that is so cool. Sweet. I don't have to be able to type anymore. As long as I can cut and paste, I'm good. So we've just put in some code, and if you're familiar with R, this is fairly similar. This keyword def means we're going to define something. We're going to define an object named area. It's going to have two inputs, depth and width. And the colon is how you delimit the object. In Excel, this would be, I believe it's name, assignment, the word function, and then you put the argument list, and then you build the function. And then what this thing is going to do is you'll notice that there's an indentation here. So the indentation is the delimiter. It's going to take an object named area. It's going to take the value of depth and the value of width, multiply them together, and put that into the value named area. And then it's going to return area to whatever calls it. And then to run a cell, you go ahead and you click this little run doodle. And if it does that, what it just did, we didn't get any error messages. We also didn't get any output because we haven't done anything. But now the computational kernel associated with the notebook named Workshop 1 now has a function in it named area. And so we can now send input to that function. Let's make it 5 units deep, 2 units wide. And you all know for rectangular channels that the area is the depth times the width. So 5 times 2 should be 10. And I think if you just run the function, by default, the notebook will evaluate it and try to return the value of the object. Sure enough, it does 10. So there's our first function. And later on, next Monday, we're going to need these other ones. So let's just get them copied right now. Let's see if that actually worked. God, I'm really liking that. No, I'm not liking it. That did not copy it. I'm still liking it because it lets me paste. I just have to copy them differently. So that has to be done with a mouse command, and this one I can use. So by separating the functions in these individual cells, you don't have to do that. It can all be in one cell. It does give you some editing advantages to do it. It also is, if your notebook gets somewhat complicated, it's a good way of breaking stuff. But if you save it, you can always unload the notebook, shut down the kernel, restart the kernel, reload the notebook, and recover from where you were. So now we have defined the perimeter function. Let's go ahead and test it and see if it works. So the perimeter needs a depth and a width. We'll give it the same 5 and 2, but let's figure out in our heads what it should be. So if it's 5 units deep, then the perimeter is 5 plus 2 plus 5. So it should be 12. And so all I did in my head was add up the wetted perimeter for rectangular channel. And now we want to run the cell. And sure enough, it's 12. And then here's another cool thing. If you decide you want to move the cells around, you just drag and drop. Now we'll get a hydraulic radius function. Hopefully it just copied it. Let me keep all my codes built. So those are still defined. Oh, it That's what I thought it was going to do. Once you get multiple deals, you're going to have to use the print function. So print here would be the same. See, the equivalent in R would probably be the message function and not the print function. So now it's returning my two values, and we want to print the radius. And it needs to know area, which is 10, and perimeter, which is 12, and we'll go ahead and we'll do a recursion in a second. Didn't like that, did it? Name radius is not defined. So what that's telling me is I haven't actually run that cell. We do it now. Now when I run this, everything is happy. And here's a fairly cool part, is I actually can do recursion, except it failed to actually follow my instructions because it's a computer and its purpose in life is to make me look like an idiot. Mission accomplished in this case. Okay, so I want to take that term, right click. That is what I was afraid of. Hopefully I don't have to manually type this. I do have to manually type it. Well, cloud computing isn't everything yet. So we give the area, the perimeter, okay, that seems right. Sure enough, that's good. And so this is considered an attractive way in that the inputs to a function can themselves be functions. And that'll come in handy soon. We'll make a friction slope function. Do a proper copy. And obviously, if you're doing these yourself, you'd be typing them because you may not have anything to copy and paste. The copy paste is not perfect, but that's still better than typing for me. Oh, notes. You'll see that the comment symbol is the like the hashtag looking thing. So there's our friction slope. Let's go ahead and test it. You can certainly take me to task on my naming convention. So I'll just make up a discharge, 2.5 Manning's End, and then go back to our rectangular channel. Area is 5 by 2. Need to know the radius. Radius is 5. Oh, radius, area, radius. So radius of area. So obviously to me, there seems to be an awful lot of typing, but when we build this into a computational machine, it's going to be putting in the various values, so we won't have to type these every time. So radius uses input of area and perimeter. Now the hard part. That closes the radius function. That closes the slope function. That closes the print function. All right, here goes nothing. And I actually have no idea what the friction slope should be. It should be, I'm thinking it'd be like a 0.0132 something or 0.003. I would think the slope under those conditions is going to be pretty small. Oh, it's really small. 1.79 times 10 to the minus fifth. Now, off the top of my head, I have no idea if that makes any sense or not. I've used these functions for quite a while, so I'm fairly comfortable that the arithmetic it just performed is correct. And then I was working on trying to fabricate a simple example for our normal flow. For normal flow, we're going to need the topographic slope. Except that was not a correct copy. So let me copy that. And we'll go ahead and add that into here. Hit the paste button. And the topographic slope function is a little bit goofy looking because I've never used it before. So we will print a value for topographic slope, and that's as far as we'll get today, but we will continue on Monday with this example. So it's a function, it has 4 arguments, so we will put our x condition, I'm just going to make them up, x1 will be 1, and the elevation of the bottom, let's put it at 100 units. Our next one will be so we'll assume these are all in feet or something. So we're going from 0 to 100 feet in the x direction, from 100 to 99. So that's a 1% slope, a unit change of 1 over 100 feet. And so we should get 1%. Okay, so we have a topographic slope and a friction slope. What we're going to do for uniform flow is we want to set those two equal to each other, and for a given discharge, we'll try to recover a flow depth, or for a given flow depth, we can recover a discharge. That's the easy one. That's how Manning's equation is taught to you back in hydrology. You know the flow depth, you know the geometry. Manning's equation tells you the discharge. But the other part of the question is, you know what the discharge is, how deep is it going to flow, which is the design question. That may not be so evident at first, but essentially we want to equate these two functions to each other, and then we can determine what the flow depth is. So if slope f is set equal to slope 0, and we have some way of changing flow depth, which we do because it happens to be right there, flow depth, flow depth, flow depth. If we set the two equal to each other, we can ingest that flow depth value until that equality is true. We'll do it by hand next time, and then we'll go ahead and add a little bit of scripting to automate that, because it's ultimately stupid to do it by hand, but we'll use the by hand to kind of see what's going on, and that will give us a way to solve for one of our 3 flow regimes that you already know how to solve using a hand calculator a whole lot easier. Part of what I'm illustrating here is that we can go from these really simple states to the more elaborate states just by building things up in pieces. So let me save that. And wonder if I can download this. Actually, I can't. There's no way it knows what machine I'm on. Well, this one is on the class server. I did nothing that's not already there. So you all, on your own leisure, can go ahead and copy that and work with it. But for next class, see if you can't get on your machine something that looks like this, and essentially get to this state down here, and then we will build from there. And our first goal will be a normal flow, mostly just to prove to ourselves we can do it. There's no practical utility outside of the class because you'd use other tools to do it. And then we'll build a gradually varied flow. That'll probably take all of next time, and we'll do them both also again in swim. So we're running stuff in parallel. Our at home, or our roll your own, if you will, and then our professional program, if you will. And then when we get to the dynamic one, that'll take a few more meetings to work through those, because the individual pieces of coding are very simple, but when it puts all together, there's a lot of things that go wrong that surprise you, and they're frustrating. So get up to this point by Monday, so that we have both have these same implementations waiting on us, and we'll use that for Monday's workshop. There'll be some lecture Monday before the workshop part, but I will allocate more time for working together on teaching ourselves a little bit of this scripting. So I want to thank you for your patience and attention. That's all for today. There is no homework, no assignments other than me telling you to try to get yourself a notebook built that looks more or less like this one. And I'm going to leave this on my screen long enough for the video to capture it, so that if you want to go and look at the video, hopefully the automatic resizing works. Oh, so that's what the inside of a black hole looks like. I've always wondered. There we go. There we go. That's what I was trying to achieve. So get a workshop notebook that looks like that. And I actually like the name that Anna picked out, Workshop 1. Maybe call yours Workshop 1 also. And we will build upon Workshop 1. And we'll use that for the next few meetings, and the first homework assignment, which won't come up until next week. We'll build upon these workshop notebooks. Okay, we got 4 minutes left. Oh, well, actually, I've already gone 6 minutes over technically. So it is time to end. Are there any burning immediate questions? And if you don't have any, that's fine. We'll pick them up again on Monday. Okay, everybody, have a great evening. Have a great day tomorrow and the rest of the week, and have a good weekend. And I will see you Monday. I'm available by email. I'm not the fastest responder, but if you email me, I'll do my best to get back to you within a day. All right, bye-bye.
Bye.
Thank you.
Thank you.
Bye-bye.